halfway through the presentation, I will explain you where this specific topic comes from, this specific wording of this topic comes from. What I want to talk about are these 4 areas: indoor particles and health effects, accounting for indoor particles, and then SOA, secondary organic aerosols, and bioaerosols. In a way, the presentation will be in 2 parts. This is outlining this state of knowledge, what we know, and how well the science is developed. But for us scientists, it's what's done, what's known, it's past. We are interested in what we don't know. And this is the area where there's still lots and lots to do. So that's why I will be more interested talking about this aspect. Air quality and health, indoor air quality and health. I'll refer here, for those who attended my first talk, to this specific quantification or accounting for health effects. This was a major undertaking, Global Burden of Disease, published in Lancet, special issue of Lancet in 2012, which looked at 67 risk factors, 291 diseases in 21 regions of the world. And what came out of this is the list of the 10 most important risk factors. Looking through this list, you'll see this is quite interesting. Some of these are clearly related to lifestyle, to habits, and so on. But on this list of the 10 most important, you'll find these 2: household air pollution and ambient particulate matter pollution. Both of these have in common that they affect respiratory and cardiovascular health diseases and cancer. And when talking about PM, particulate matter pollution, we are talking specifically about PM 2.5. It was quantified in terms of PM 2.5. To those who may not be familiar with this terminology, is mass concentration of particle matters with aerodynamic diameter smaller than 2.5 micrometers. So this is globally, and I think it is quite interesting that out of these many risks, the 2 aspects of air pollution came up this strong and this important. We could talk more about this, but what I'd like to now point out that from the website of GBD, you can find El Dorado of all kinds of information, and you could look specifically at different regions of the world and specific countries as well. And by the way, there's an update of this going on, and the first paper of the new update has already been published by Lancet, and within the next few months there will be a new version of this. What I'd like to point out is, when looking specifically, zooming now on this part of the world, at your country, what are the risk factors here? You see similarity with the previous list, but also differences. One main difference is that while ambient particulate matter still is among the 10 top and actually went up higher, what disappeared from this list is household air pollution. Why? Because household air pollution really relates to the environments where biomass burning takes place. We are talking open fire burning, this kind of environments, which are significant in developing countries. So the fact that it doesn't feature here on the list of the 10 means that in Israel this aspect is not that significant. Therefore, when talking about indoor aerosols, indoor air, I will not be talking about household fuel pollution in this sense, but I'll be talking about other indoor sources. So this is ambient particulate matter. Ambient means outdoor. How this kind of estimates are done? There are many, many steps of this, and one significant is to link concentrations with exposures. In the older edition, went too fast. In the all the edition of the WHO guidelines, this was how it was linked through this linear relationship. So in this case, I don't think you can see it very well. So this is PM10 concentration, particulate matter smaller than 10 micrometers, and various health effects, so mortality, hospital admission, and so on. The important factor of this is that all these relationships are linear, that they finish here at 200 micrograms per cubic meter because that's where the data were. And they were all extrapolated to these low values because then these values were not available. Since then, many studies have been done. And here, as you can see, there are relationships for two specific health impacts, acute lower respiratory infection of infants and ischemic heart disease. And what you can see that this relationship are not really linear in the whole range. There are still, if you look at just this particular range, which is covered here, they are linear, but at higher concentration, they level. And then they have different shapes at the very low concentrations. But now it is actually data from the very low concentration, basically showing that there are no thresholds, which means that the studies conducted at whatever low concentration, they still found health effects. So this is what we know, and this knowledge is progressing fast. There are more studies. There are still things we would like to know better, but this is very well known. But one important aspect to remember it is this is based on ambient air, not on indoor air. So what we are saying is that there's been all these large databases available on outdoor particles or pollutants. These data were used for prospective and retrospective epidemiological studies. And these studies show this very clear link between outdoor air pollution and health. However, we spend the majority of time indoors. We spend 90%, if not more, indoors. So how come it is that it is the outdoor air which has such an important and strong impact? Well, if we think about this, and if we look at this little demonstration, we've got the house, we've got this example of outdoor air pollution. The pollutants get from outdoor air indoors. They undergo all kinds of transformations here. It all depends on many parameters: air exchange rate, penetration rate, filter efficiency, if the building has mechanical ventilation, in relation to particles, deposition rate on all the surfaces, then other processes like particle coagulation, reactions, and so on. At the end, we've got a different characteristics of the indoor aerosol. But nevertheless, it is the aerosol coming inside. How much of this aerosol is coming inside? One way of quantify this is by indoor to outdoor ratios. A simple concept: we measure indoor concentration, outdoor concentration, we calculate the ratios. So if we just focus on naturally ventilated buildings, houses, and in the absence of indoor sources, so we are just interested on that outdoor-indoor relationship. The general shape of the relationship is this. So with this particle size in logarithmic scale here, the ratio has this shape. And we can very well explain this. These particles, the concentration indoors, ratio smaller, concentrations indoors smaller. The smaller particles, very efficient removal mechanism by diffusional processes. On the other hand, for larger particles like over 1 micrometer or larger, there are other processes, impaction, interception. So the least of the forces acting in this range. And then if you look at these values, which came from literature reviews, you can see that for particle number concentration, which means the smaller particles, the ratio is about this, 0.56, 85, 64. One other way of thinking of this would be, you could say that 85% of PM2.5 from outside is inside. That's a very simple concept. But it shows how much of this is inside, and these are real studies. So this explains how important outdoor air is. There are still complexities with this, and if we dig deeper into this, we find out that you can't just look at the ratio, but we need to do a little bit more. What this is presenting here is one of aspect of our studies conducted in Brisbane at a school environment. And what we did, we put, if this is that conceptual school grounds, we put all kinds of devices to measure. There should be even more of this. So school grounds, we measure particle and pollution characteristics at these 3 different sites, and now, and also indoors. So now when we can see what is the impact of measuring here versus measuring here or versus measuring here. You can see that in this case there's a busy street here, so less impact of the street, let's say here. So what we've quantified for these schools, there were 25 of them, so if we calculate the ratio to B, that central site, so on that whisker plot we already can see that there is a variation between C and A. It's not a huge variation, but nevertheless there is a variation. So therefore, if you are thinking about indoor to outdoor ratio, it is the question where that outdoor measurement is conducted if you are thinking about a specific microenvironment. But as I said, this knowledge is emerging. I found this as an interesting paper published on this kind of environments. Now we are talking about how high risers and winds say from this direction what happens. And we can see that this eddies around the buildings. So again, if we want, let's say in this building, calculate indoor to outdoor ratio, so which outdoor measurements are we going to take? Just measurements here, measurements there, and so on. So even this aspect, indoor to outdoor, has its complexities. But as I said, we are certainly developing a good knowledge about this kind of things. So this is the impact of outdoor on indoor. In this case, do indoor pollution sources matter? You can say, well, if outdoors has such a pronounced impact, maybe they don't matter at all. Again, a graphical representation what happens inside, pollutants emitted from a source, be it a stove or whatever, undergo all kinds of processes, and here we are looking at different aspects. We are looking at emission rates of these indoor sources or formation rates of particles, for example, again, air exchange rate, removal, deposition rate, coagulations, and so on. So it's a whole complexity of the dynamics taking place inside. There was an interesting assessment conducted under this EU project, indoor air contaminants and contribution of indoor sources in Europe. This is a table, and I'm showing just for the time being a part of this table. So we are looking at specifically on PM2.5. Now this is a value long-term WHO indoor air quality guideline value. Now, if the concentrations are typical means 10 to 40 micrograms per cubic meter, then the indoor source has about 30% of contribution, and the outdoor source has about 70% of contribution. So for typical concentrations, it's the outdoor source which is the most important. But if we look for high end of concentration, like 100, 300, then 90% of contribution come from the indoor sources. So indoor sources are important. Now I'm not going to talk about the rest of this table. This same consideration were done for other pollutants which are covered by the WHO indoor air quality guidelines. So using this information, there was an assessment conducted to look at DALI, which is disability adjusted life years, means life years lost to death, and years lived with disability if, if a person acquires a disease. We have here all the different European countries, and we've got the blue and red. Red is contribution from indoor sources to this DALI, and blue from outdoor sources. So on this you can see that both of them, both indoor and outdoor, have contribution to this global burden of disease quantified as DALI. You can now ask, okay, which of the sources, which of the exposures are important? And there are two ways of looking at this. In this case, from the same report, it is key exposure agents, and there are these different agents, and you can see that the biggest chunk of this pie is combustion particles, which is outside. You can also wonder why pollutants like this, VOCs, has played such a small role. Well, we don't know whether they play such a small role. The reality is that they haven't been enough data. So the data is based on what's available, but new science may add new picture and change this slicing of the pie. Another way of this is to look at the key sources, and as a key source, again, ambient air is the biggest part of the pie. So this is the impact on indoor to outdoor. Now this is supposed to be making noise, changing the angle of discussion, so we look at something very different now. Quantification of indoor aerosol. There are many different ways of doing this. Say, taking so-called mass number balance equation, looking at aerosol dynamics, or combination of different models, including CFD modeling. I will not be talking about quantification of such, but I will qualitatively talk about quantification. Otherwise, we'll have to be here until tomorrow. Just for a moment, we'll focus on this mass balance equation, because it is in a way the simplest concept, but it brings up some issues. It's a long equation, but it's quite straightforward. So we've got the indoor concentration, we've got outdoor concentration, and we've got penetration factor, air exchange rate, deposition, flux from indoor sources, emissions, volume of the interior. So basically, we have several different terms. This is coming from outdoor. These are the losses during, as a result of air exchange rate and deposition. This is contribution from indoor sources. These are reactions. Simple concept. One could say, all right, with this we can, provided that we have all these parameters, we can just quantify everything in any environment. Well, is it always really very useful? Let's look at this building here, which is how it looks. And it's a particular building in Sydney, quite futuristic view. But if we were to calculate mass balance equation for this building, you can imagine how many different zones and places and so on would. So where would you put your monitor? Which exchange rate in which place? So it's basically the concept of mass balance equation to this building is not very practical. When we made a jump to a very, very different environment where we also conduct studies like this house in Bhutan. So where do you put your instrumentation? This is the stove, and as you can see, that smoke is going this way. So again, mass balance equation in this kinds, it's not something which is a very useful concept. All right then, let's put monitors everywhere. Let's monitor all these parameters. This is one example of one of the early studies on this, and you can see lots of places when this office environment monitoring was taking place. Lots of different parameters, but really air quality parameters and specifically particles are very rarely monitored. But still, this is the future. This is coming, and in no time at all, we will be surrounded by all kinds of monitors, whether we like it or not. For example, having cameras all around as may not present the pictures we would like to. There are different monitoring challenges in these environments. This is my PhD student Tenzing doing measurements in this environment, so you can see how many curious lookers he's got here. But in an environment where there's no electricity, for example, you can imagine that we are facing different challenges. But nevertheless, in terms of the monitoring, the world of monitors, the world of monitoring is improving, and we can get lots of data. Now, we can then move from that simple mass balance equation to aerosol dynamics, and here it's just a qualitative way of presenting aerosol dynamics. We've got particle coagulation, we've got particle evaporation and condensation, we've got particle deposition on vertical surfaces or on horizontal surfaces. Different processes contribute to this. And that last one here is what? Transport, all things which take place during transport. There are equations, there are textbooks going back to many decades, so we can calculate this reasonably easily if we have all the right parameters. So as I said, I'm not going to discuss the individual equations. But the third aspect of that quantification, which I mentioned, are models. And there's a plethora of different type of models for calculating anything we want, we dream about, and in any way we want to do this. So it's a list of several models. So it's just another area expanding of the models. One interesting aspect of this modeling is presented here. More and more the models, and this work is linked, of air quality is linked with energy and energy conservation, or the other way around. The big focus is on energy, and occasionally there's looking also on what's the situation with indoor air quality. So if we try to optimize what's happening in the building, in relation to building activities, energy use, but also on the outside sources, we can say, let's ventilate the building, let's get rid of anything generated inside. But then we are bringing all these nice things inside. So, so that's a bit of a problem. So there are this kind of models. This is, again, one of my PhD students who came up with this model for optimization, and here is the optimization of energy and air quality. So he looked at, in this case, on particle number concentration, indoor, outdoor, measured what the model predicts, and then CO2 and so on. So this is that energy air quality, but as I said, it is the energy which is driving this kind of things, driving to the point that this went outside research domain to public life. If you see a cover of a magazine like Time talking about the smart home, then you see that it's not just research. But what does it mean, a smart home? It means energy efficient, it means self-sustained, in particular making our life easy and enjoyable so we don't have to do anything, and this way less exercise, so I'm not sure whether this is so good. But smart home now, it's not really understood as a home which caters for good air quality. So it's another bit of an issue, but as I said, there are now attempts, and we can now link this to energy and air quality. So this is this modeling approach, and one other aspect of the modeling, just to show how it works, CFD model, computational fluid dynamic modeling. We can probably recognize, David, this place, yes, my office. And they were very keen students to calculate if there was a printer placed in different locations, what it would do. We can generate lots and lots of very nice images like this. It is very demanding because you need to have all the parameters for this, and then you change slightly something and the pictures change. So you can generate another 100 of pictures. So that's, that's very nice. But the summary of what I've said so far about this quantification is that if we put our tools together, we can basically account for every particle of the interior of choice through whichever of this modeling, measurement, and so on. But interior of choice. So it's not something that we'll develop for this building and then we can use for the building next door, because next door is different and it will require a lot of computational and work. So how all this has all these practical applications to real environments? Relevance of various processes, so many parameters needed, and the parameters can change rapidly. We'll open the window, the position here will change. The parameters are building specific. So all this science is there, but the applicability of this is a question mark. The title for my presentation came from this, the relevance of various processes. In, for example, this room, is coagulation important? No, it's not important because concentrations are very low here. Air exchange rate takes care of this. So, but many people modeling this will put all the processes into very big model, calculate this, something will come out. I came to a very heated discussion, a group of us during a conference a year and a half ago, what's important, and where now a group of us is writing a review paper on this. That's the reason for the topic. So there is a really huge gap between what we can do using aerosol science and predictive modeling and what is done in practice. Who is to close this gap? Scientists or the practitioners? This is another issue. So now I move to the areas where science is still developing. I've already mentioned on during my first presentation, when talking about all these different environments, I keep clicking the wrong button here. All these different environments where all the different things happening, yes, there are 2 or 3 important things which are characteristic to all of them. Transient nature of the indoor source operation, role of the background, and secondary aerosol formation. So transient nature of the source emissions is this. If we operate any of these indoor sources, they don't operate all the time. They operate for a short period of time. We print something, done. We made a toast, someone smokes a cigarette, done. It's a short process resulting with very high concentrations. Like, for example, on this diagram, time series of concentrations of particle numbers, and PM2.5 in a residential house. So was it 48 hours or 24 hours? 48 hours concentrations. Now, what you can see, so this is sitting on this background. The owners were not here, so this is coming background from outside. And then they are cooking, and you can see these big peaks. So they don't last for a very long period of time, but the concentrations are significantly above. It could be orders of magnitude higher than the background. So this is something very important to consider. And as I said, I won't talk more about this, but this will come in the 2 aspects I'd like to focus. So the questions here, how to account for these peak concentrations? Real-time measurement techniques, only real-time, because if we do any averaging, these peaks would disappear. Diary of activity, same kind of monitoring what's happening. But there's another question here. Is this important? What impact does it on health? Does it matter that we went up through this? That's our exposure. Or if we look at the average exposure, that's where there are lots of questions. But with this little background to this, I'd like now to focus on SOA. When you look at this picture, it doesn't sound like SOA whatsoever. It's just an issue of particles in an office. It's an office here, and the question was, is the ventilation filtration system of the building efficient to take care of pollution from a busy road, freeway, which is next to the building? Well, the government wanted to know this. We work with them closely, so I said, let's do it. Nothing interesting would come up whatsoever, but collaboration with them. Now, as we started doing this, this came out and started putting our hypothesis and all what we were doing under a question mark. This is, again, time series, particle number concentration. This is indoor and outdoor. If we look at that outdoor, this red, it's changing. Of course, there are vehicles outside, it's changing. But what's happening indoors is behaving as what I just a moment ago said. It is these big peaks. It's an office environment, completely mechanically ventilated, strict regulations in Australia. Nobody would dream smoking of a cigarette anywhere inside. So where is this coming from? We searched through the whole building for a source, and no source was to identify it. Eventually,